You're listening to the Banana Data Podcast, a new podcast hosted by Dataiku. I'm Triveni.
And I'm Weyl.
And we'll be taking you through the latest and greatest in data science without taking ourselves too seriously. Today we'll be focusing on biased data in our digital assistants, the power of AI personalization, neural networks, and the hardware that powers all of our data science efforts. So Weyl, to get us started off, let's talk about this article I sent you earlier this week called How Digital Virtual Assistants Like Alexa Amplify Sexism. And it's by Morgan Meeker of 10. And in this article, they talk about how Google devices and Alexa and Siri and all these digital voice assistants are actually perpetuating some of the most, harmful stereotypes and biases that exist in our world already. And I guess the most prominent example of this is when someone in 2016 asked Google, "Hey, Google, are women evil?" And the response, was this very misogynistic statement that had come from a blog Google found while searching the internet. And I think it's interesting because we like to talk about how AI is going to be neutral and not really hurt us going forward. But in fact, I think what we're starting to see is that because we're giving our systems such variety of data that's not always good, we're getting back results that are not always correct.
Yeah, I mean, this is depressing, but as someone who works in the space, it's also maybe not surprising, right? Machine learning tools are just learning what we tell them, and what we tell them, it's getting from data sources that we use. So it's unfortunately not really that surprising to me if Alexa is just scouring the web. If there's some hate speech on the web, it's going to take it as input and then try to use that as output. So I think either we need to be better and just kind of monitor this, or maybe better yet, someone could come up with kind of some systematic solutions to really resolve this.
Yeah, and it makes me wonder, how can we push these companies themselves to be thinking about this more as they develop these systems, right? Google has stated that, okay, we didn't actually do anything wrong by promoting that blog or that statement, because our search, this is a quote from them, our search results are a reflection of the content across the web. And so it's not necessarily Google and Apple's and Amazon's fault that all of this stuff is out there, but do they have a responsibility to be filtering things or maybe fine-tuning things so that we're not perpetuating certain biases?
Yeah, I mean, I was actually surprised. I'm not the biggest user of these sorts of virtual assistants, but in that post they mentioned that originally when you made derogatory comments to Amazon's Alexa, the responses were, shall I say, maybe not what most would assume are favorable responses. But then over time, they kind of retrained Alexa to really, stick up for, quote unquote, herself, which is an interesting and I think kind of promising progression there.
Yeah, and so it gives you some semblance of hope that, okay, these companies are starting to listen to things a little bit better. But then at the same time, they're still dealing with that problem of bad data, right? So one of these examples is that if you ask the Alexa app, what are the symptoms of a heart attack, right? The response is going to be chest pain, shortness of breath, feeling weak or lightheaded. But that advice actually doesn't include symptoms that are more common for women, like back pain or jaw pain. So I might ask, what are the symptoms of a heart attack for myself and not for you, Will, but it's not going to actually help me out that much.
Yeah, I mean, the optimist in me thinks that, we don't know all the jobs that are going to exist in 1 year or 5 year or 10 years time. So this to me seems like a really great use of human resources, right? As people worry about AI and ML automating away jobs, I think we definitely need humans in the loop to be doing exactly what you just described and double checking these systems and saying, hey, this is not fully representative of all the information that all of our users need. So that would be real good.
Yeah, I mean, so this actually links back to another thing that they discuss here, which is the idea of the Data Nutrition Project, which is a collaboration between some folks at Harvard and MIT. And what they're doing is starting a push to include data on the data itself that you're using for your models, right?
So like metadata type stuff?
Yeah.
Data about the data?
Data about the data would be metadata, correct. And so, they're listing things like, this is where the data was collected, by whom it was collected, who paid for this, and in this data, which groups are maybe missing. Because one of these problems, as the chest pain or heart attack issue surfaces, is that so much of our data just forgets about a whole subset of people, right? Forgets about women, forgets about people who might not be the majority race or class in their home country. And it's actually something that has been really well studied by Caroline Criado Perez, who's written a book called Invisible Women, right? That talks about the fact that so much of our data is just missing not only data about women, but like data about Black women or data about Black men, the intersectionality pieces that are missing from our data.
Yeah. To your point about the nutrition facts, it makes me think just about the protocols that we use in our day-to-day work as data scientists. So things like comma-separated values, so CSV files. So there is a protocol, there's a standard that each cell is delimited by a comma, or things like JSON files. And actually another thing, maybe I'm playing optimist today, that gives me a little bit of hope is in some of our work with clients, I sometimes see that they will mandate in their organization that metadata is attached to the data that they're using, right? So if you want to use this data in a particular project, there's a field, wherever that data is being passed that says, what is this data about? And if that's blank, you can't move forward. And so I think the more we can kind of institutionalize that process and use data protocols to help, that would be, I think, progress.
Yeah, but I also think that's what we as data scientists can do. When really this issue of the bad data starts much earlier in the pipeline, right? It is dependent on the folks who are going out to collect data about how our roads are used or how people interact with Alexa or whatever it might be. It is dependent on them to make sure we're collecting the whole swath of information that we need, right? And not just the swath that's easiest to get or the one that we think matters the most.
Yeah, that makes sense. I did actually check out this article as well, read through it. And one of the other pieces, I don't know if you remember this, that they spoke about was this idea of the perfect answer, and particularly as we transition to voice as kind of this dominant interaction with technology. So if you think about these virtual assistants, we're often not typing things to Alexa. I don't even think it's possible to type things to Alexa. It's an audio interaction. And so when you ask an audio question, you just get back one answer. And so this idea of the perfect answer, you don't have time for 10 different Google search results. You get back one answer from Alexa. And I thought that was super interesting how they said, well, that's actually a threat, because instead of just getting one answer that's perfect for you, well, what does it mean to be perfect for you? Maybe it's leaving out a lot of information. It's maybe giving you a biased source, and that's actually hurting you.
Yeah, and actually when I read that, I was sort of wondering about echo chambers, right? Because if over time these voice assistants need to learn how to give me, Triveni, my perfect answer, it's going to learn what I want to hear. And as a result, keep giving me that, which might not actually be accurate information, which might not actually be the actual correct answer, even though it's perfect for me, right? And so we fall into this trap of perpetuating our biases and echo chambers. That is similar to sort of what we see with Facebook feeds, Twitter feeds, Instagram feeds that are tailor-made for you, but don't let you expand your mind out.
Yeah, I feel like no one's figured this out right yet. Like how to give you what you want while at the same time expanding your horizons and educating you and pushing your limits a little bit. So that's really an open question in the space as far as I can tell.
Sounds like a good side project for you, Will.
Yeah. This article, this idea of the perfect answer, kind of makes me think about another article I read recently from the Stitch Fix blog. So here we're talking about the perfect answer. This blog post talks a lot about the perfect model, but it's by Patrick Glen and Divya Prabhakar. It's called Your Client Engagement Program Isn't Doing What You Think It Is. And there's a lot of really interesting points in it, but to this idea about just one perfect answer and that kind of being a false paradigm, this blog post kind of hates on A/B testing or split testing instead of saying that you should just search for one sort of client engagement program because one client engagement program will be superior. Patrick and Divya say, you have different users and different users will respond in different ways to different client engagement programs or any sort of services that you are providing them. And that's so obvious, but so often we're doing A/B tests and we're searching for option A or option B, which is superior. And so they kind of throw that all out, which I thought was really interesting.
So what are they suggesting instead, like multi-arm bandits?
That's exactly right.
Oh.
So they are suggesting the use of multi-arm bandits. So for those who aren't aware, multi-arm bandits, the analogy here is imagine you're at a casino with multiple slot machines. So instead of just having one slot machine arm to pull, you have multiple slot machine arms to pull. And which slot machine arm should you pull? Because you don't really know the distribution of rewards at any given slot machine. And people often talk about in this space the trade-off between exploration and exploitation. So if you know that this slot machine is pretty good, should you just exploit that and keep going back to that slot machine? Or should you try another one that you're less familiar with and see maybe actually the reward distribution is higher there? So they talk about multi-arm bandits, as you say. And increasingly, I've read and heard more in the space now about contextual multi-arm bandits. So basically distributing the policy that's sent to particular clients, but also taking into account some sort of context. So that is, if I know that you're really interested in Instagram and know that you're really interested in Facebook photos, maybe I'm going to send you a picture or a email that's heavy with pictorial content. Whereas if I know that you just read lots of blogs online, I'm going to send you an email that's just text heavy.
Great. So going back to that data privacy issue too.
No. So it's complicated.
Well, this is interesting because I've actually used Stitch Fix in the past. And I think I used them before this article came out. So I don't know if they were using this strategy on me or not. But I noticed that the first couple, so Stitch Fix essentially is a service that sends you a box of clothes or shoes or whatever apparel that you want to wear after you've done a survey of like what's your style and, what's your fit and all of this that you like. So you send in that survey, they send you a box of 5 items that you can wear. And you can choose to buy all of them and get a 20% discount, or you can choose to buy, however many items you want. The remainder you just ship up and send back. Cool. So I did this a couple times, and my first few boxes, I was pretty much going for 3 of the items each time. Mm-hmm. Like, 1 or 2 of these don't really fit, or I don't like the color, or whatever. And I don't think I ever really gave feedback on why I didn't want those items, but I just sent them back.
Implicit feedback, right?
Sort of implicit feedback. There you go. Yeah. And then I realized and I noticed that after the first few times, I started getting these boxes where I wanted the whole box. I was keeping everything in the box, getting that 20% discount, also awesome. And I'm curious to know if this was one of those cases where they ended up doing a multi-arm bandit and they found gold, right? They explored a little bit and they found gold with me. Or if it's something that it was like one size fits all, that they were just trying to refine, right? One model that's going to be for everybody, but with refined inputs.
Yeah, no, I mean, that's a great question. And so I think that would probably, to me, be definitely a case where they're thinking more about personalization, right? Because your own style is very different from my own style, probably. Right. So they have to be personalized there.
Yeah.
And I think another point that they make in this article that I thought was also interesting to me is that this idea, if you think less about the clothes allocation, more just about traditional things like, ad placement or, particular email content, even if you find in an A/B test, many organizations might find that one particular tactic, A or B, is superior. They do the random allocation, they run the stats, and they see that maybe tactic B is the best. You don't know for how long that program will remain the best. So that's another, it's obvious, but so often you say, okay, we're split testing these 2 alternatives. We found the best one, therefore it is the best, full stop. And using this multi-armed bandit or this contextual multi-armed bandit, it's a nice way to continue learning. So you can continue to throw in new alternatives. And then if you think about, if anyone at home is familiar with things like the epsilon greedy multi-armed bandit approach, I would just encourage our readers our listeners to Google that if they're interested in learning more.
Sounds amazing.
Maybe we can do an explain in English, please, the epsilon greedy approach to the multi-armed bandit next week. But you can, epsilon % of the time, point your audience to some brand new tactic, some brand new alternative. And then maybe you're going to find that actually tactic C or tactic D, these things are really driving growth for your organization. In general, I think that kind of going back to the previous article, to me, this is just this really interesting trade-off where the future of artificial intelligence, is it one model per person? That's really attractive in some ways, and that everything's personalized and we live in a world that's tailored to us. But then going back to the sexism and AI piece, there are so many dangers there too, where we obviously get stuck in our echo chambers. So kind of the trade-off between customization and the risks and benefits therein, I think these 2 articles do a nice job to point out. So I'd encourage listeners to check them out.
Yeah. Thanks for sharing, Will.
Yeah. Okay, listeners, now it's time for my favorite part of the show, in English, please. So Triveni, if you don't mind, could you please explain neural networks in English, please?
Sure. I'm gonna try this out here. This is gonna be fun. So when we talk about neural networks and machine learning, what we're talking about are systems that are meant to replicate the way that humans process input, right? So if I show you a picture of a cat and a dog, you have a set of rules in your mind that tell you how to understand those two things as different creatures, right? Now in machine learning, neural networks are going to accomplish the same thing by creating weights for those inputs that then become rules on how to process new information. So if we think about biologically, our brains have these individual neurons that are constantly analyzing inputs and firing off information according to the rules that we've taught them. And in a machine learning in the neural network that's a machine learning neural network, each neuron is essentially a mathematical function that then takes that input and produces an output. So these neurons are arranged in layers or groups, and so we can say there's like 10 neurons that are analyzing inputs in the first layer. So in that first layer or that first step of the model, one of these neurons gets an input that says, hey, this animal has a small pink nose. And that neuron is going to apply a set of rules or weights that determine, okay, well, this is about a 90% chance that this is a cat then. And so each of the 10 neurons in that first layer are going to send outputs to the second layer neurons who are going to process that information according to their rules and then pass that information on to the next group of neurons. So it just goes down this chain of neurons or layers of neurons. And so the number of layers and neurons can be really large in some cases, like image recognition. But after applying all of these weights and rules through all the different layers, the model is going to give us a final output. Like, okay, this is a cat, and that's based on the rules and thresholds of the complete neural network that came before it.
Awesome. Thanks for explaining that, Triveni, in English. And speaking of neural nets, today we've invited Mark Buckler, a PhD candidate at Cornell and author of this article, How to Make Bad Deep Learning Hardware, to tell us a little more on what's sitting on the back end of our data science efforts.
Hey, Mark, welcome to the podcast. Can you tell us a little bit about yourself?
Hi, yeah. So I'm Mark Buckler. I'm a fifth-year PhD student. I work in Adrian Sampson's Approximate Computing Lab here at Cornell University. I've worked on a variety of different things in my career, but my PhD primarily focuses on hardware-software co-design for embedded computer vision. And that's very closely related to data science because, for example, my most recent work proposed using video compression techniques to reduce the time and energy required for CNN inference. So neural networks are a large part of what I do here.
Okay, whoa. I have a lot of questions already. So yeah, let's just dig into it. You said you're at the approximate computing, is that right?
Yeah, that's correct.
What the heck is that?
Yeah, so approximate computing basically means that if you're willing to accept a certain amount of error in your computation, then that basically, if you're willing to accept that, then you're able to get a significant amount of savings in computation. So, for example, take that video compression project that I was talking about. So, convolutional neural networks are often used in things like, self-driving cars or perhaps drones. And so, that's really exciting, but these applications are often energy constrained. They really need to worry about battery life. So to save on battery life, one of the things that we've developed is basically the ability to sense when the scene visually is very similar to previous scenes that it has observed in the past. So this is normal for natural video because the one frame is very similar to the previous frame. And so we can use this information to significantly reduce the amount of computation that's required while still getting a result that is very, very close, but not perfectly exact, to what you would have gotten if you just did the computation normally.
Yeah, this kind of sounds like what data scientists deal with a lot too, where we have these bias variance trade-offs, right? I want something to be a little bit more accurate versus speedy, or the other way around, right? Where I want a model that's going to train fast and is going to get me about 90% of the way there.
Yeah, playing off on that accuracy versus time, energy, and cost trade-off is absolutely in line with what we do.
So for the data scientists listening at home, I'm a little bit familiar with the idea of quantization in neural network training and shipping. Is that kind of related to your work?
Yeah, absolutely. Quantization is definitely one of the many things that we work on. That's one of the things that is most sort of well known because it is such an idea that can be used very easily, I suppose, or not necessarily easily, but it is one of the most clear-cut ways to save on computation because it basically saves both on the time to do the actual computation itself, but also reduces the average amount of bandwidth you need both for your weights and for your activation.
Okay, so I want to back up a second here. Why should I, as a data scientist, even care about this, Mark? Like, it's nice that you're here and all, but I'm not sure why. No, it's great to have you, but I just don't know why this part matters to me. I just need to do my models and run my scripts, and I'm fine.
So, as a PhD student, I am absolutely comfortable with answering the question, why should I care? Yeah, it's something it's totally normal to ask. So basically, the answer may be that you don't care, and that's totally fine. But the specific reason why you would care would be if you're building a model that is going to be resource constrained in some way. So, typically that might be that your end system, wherever you're doing your deployment, is going to have some certain budget in terms of like energy consumption, time, in terms of latency or throughput, or money in terms of, maybe you care about how much cost will be to your end user, whoever's buying your product. And of course, you can always trade off all of these things by giving up a certain amount of accuracy. But if you have some, you need to meet some cost budget to also have some accuracy, that's the situation where you're going to begin caring about hardware because trade-offs are going to sort of force you into having to think more about how you're designing your system.
So like for, Alexa, Google, Voice, all these guys, they're trying to optimize that hardware so that the models are also performant, but that they don't need to ship out like, a 10-pound computer full of computer chips or whatever.
Absolutely. In fact, embedded systems are one of the primary reasons why people care about hardware, which of course is the reason why I'm doing my thesis on embedded systems.
Oh, great.
Yeah, and just to be clear, and please correct me if I'm wrong, but my understanding is that oftentimes in these intelligent systems, there's a trade-off, at least historically there has been, and I'm sure you know much more about this and kind of the future state of it than I do, but between doing the inference kind of on device or on a central server. So I believe that for some common phone speech recognition systems, when you say, hey, Siri, that listening is actually that computation that is that listening is occurring not on your phone, but it's occurring on a centralized server. Am I correct in my understanding or totally off there?
No, you're completely right about everything you said there. And there's also an interesting thing associated with that we haven't mentioned up until this point, which is the idea of privacy. So, when you're doing these kinds of voice communications, a lot of systems, Siri, as you mentioned, does do this locally, or at least it does it locally for the Hey Siri part of that. The reason why they optimize for that is because it needs to be always on, always listening for that, and they turn on another system once, it's turned on, that'll do the cloud-based communication. But being able to sort of keep your voice communication to your local system is of course very desirable. Because you don't necessarily want that data going to the cloud. So this is an additional consideration for why you might care about hardware, because if you do need to do it on device, of course, everything becomes more complicated.
Well, this is great. Did you listen to our last podcast? Because you're tying right into all of it. Last week we spoke about federated learning, right, which is this idea of sending out models and letting them run locally and then sending back the results so that folks don't have to share their actual data. But what you're saying also kind of reminds me of this these new developments sort of in tiny chips that can optimize neural networks, right? And I'm curious to know a little bit more about what is the what's breaking through in this hardware world, right? And how is that actually going to affect us as data scientists, right? Like people talk about GPUs all the time. Not quite sure what that means still. I mean, I know what it means, but why does that matter to me? Curious to know a little bit more about that.
Sure. So if I feel free to correct me, but I kind of heard two questions there. One was what is emerging in the hardware space, and the other was what is a GPU and why should I care about using it?
Yeah. So let's start with the second one first.
Okay. Sure. Yeah. So basically, like GPUs are distinct from what most people think of as computers, which are usually single core CPUs. And they're distinct because, CPUs can only run one process, can only process one data element at a time. CPUs, of course, work really well for most applications because most applications sort of depend, each new operation often depends on the previous result. But this isn't true for graphics. And so the GPU, that graphics processing unit, they initially emerged as a solution to the problem of graphics because when rendering a given pixel, you often don't really depend on the results of another pixel. So waiting to render pixel number 2 until after you've finished rendering pixel number 1, is pretty inefficient. And so GPUs emerged as a solution to this problem because they can perform many operations all at once in parallel. So where this connects to data science is basically neural networks, and to a lesser extent maybe support vector machines and various kinds of larger models. And the reason is because basically similar to how these individual pixels don't necessarily depend on each other, the same could be said of individual neurons within an artificial neural network. So for this reason, actually, neural network computation maps very well onto GPUs, just as graphics do. And so this is the reason why people began starting to use GPUs, but they only began doing this once they got to the size of model that sort of required, faster training. And so this is a somewhat recent development, but that's sort of the, maybe a long-winded story, but the story of how GPUs got involved in data science.
That's a fantastic explanation.
That was great. I mean, you should come on the podcast more often and tell us things, please.
Happy to come back.
So I wanna maybe circle back to a bigger picture question here. How can we as data scientists better support you as a hardware scientist, visionary, genius, what you are? I don't even know what it is. It's amazing what you're doing. So how as we as data scientists, how can we help you, Mark?
Yeah, sure. So I guess the high-level answer to this is sort of a very easy thing to say, which is just communication, but I want to back that up with some very specific sort of things that can be done here. So, in terms of communication, it's really sort of a two-way street, right? So we need to talk to you and you need to talk to us. So in terms of, what you guys can do for us in terms of communication, thankfully you guys are doing great. And the specific thing that's important is publishing often. And publishing, deeply. So not just sort of saying like, we have these sort of very high level descriptions of networks. No, like give us the details because that's sort of where we become relevant, right? So at the high level, it's impossible to tell what hardware is going to really work well. But if you give a lot of details, then that's going to be really exciting for us. And thankfully, I'm not sure why, but there really has been this huge sort of push for, using archives. So we're even getting faster results in terms of, what's going on in the world. And then people are releasing models on GitHub. I mean, it's really sort of exciting to be a part of this research space now. So that's one thing that would be really helpful. So in addition to this, though, one thing that maybe folks could do a little bit better on would be to read our papers. So to try to learn about, the new hardware designs that are coming around the corner. And, that's going to really help you sort of understand how to design your systems in a way that will sort of match well. And, of course, the best thing to do is to work directly with hardware designers, but of course we don't all have the resources for that. So I understand that that's not possible. But trying to learn about the new kinds of hardware that's coming around the corner will really help us and also help you.
Yeah, I think this is a great point, and kind of an underserved aspect of the data science community is, at least when I was, and still try to up my skills in this domain, I don't come across, maybe I'm just looking in the wrong places, and you or any listeners at home, feel free to correct me, but I don't come across all the good resources about kind of hardware construction and the intersection between computer hardware and data science. So another kind of call to our listenership, please, if anybody's out there, just like Mark, who really knows this space, feel free to make some lay posts for at least people like me. I don't know about you, Triveni, but I would love to kind of get an easy introduction to this to upskill.
Yeah, it really sounds like what you're talking about is collaboration in a much different way, right? Because we can think about data scientists collaborating on a Kaggle project or even at their jobs. But, the collaboration between people who are doing cutting edge tech work, hardware work, and folks that are trying to create new models, more efficient models, whatever it might be, really there's a space there that kind of needs to be filled, it sounds like.
Yeah, totally. I think it would be really exciting to do something like that.
Great. Tell us what's the newest sort of thing on the horizon for data science and people who build hardware for data science.
Yeah, totally. So, one of the things that is definitely coming out, or at least is coming out in more popularity now, are systolic arrays. So these were developed in the late 70s, early 80s, but have come much more into vogue due to support from Google and NVIDIA. Google with the introduction of their TPU, and NVIDIA with the introduction of their tensor cores. So what systolic arrays are basically is you can kind of think about them like physical hardware accelerators for one specific purpose, which is matrix multiplication. And thankfully, matrix multiplication, while it is itself a very specific computational kernel, it is also sufficiently general so it can support many different kinds of neural networks. And this includes things like convolutional neural networks, LSTMs, GANs, various kinds of networks, all sort of have this core element, which is the matrix multiplication. And so if you make that core element fast, then the entire network as a whole is fast.
Cool. So how does the hardware actually make these networks faster?
Yeah, so the hardware basically takes into account the idea of data movement. So we were talking about the idea of operations and how maybe if you have fewer operations, you can be faster. But if each individual operation requires a long latency or waiting time for it to finally get the data that it needs, you may end up being slower. And so we sort of take this to the extreme with systolic arrays by saying, listen, we know that matrix multiplication is going to be the specific kernel that we are going to be performing. So we are going to optimize the actual physical wires within the system to create data paths that are optimized for that specific use case of matrix multiplication. So rather than constantly going back to DRAM or to even some cache to get some kind of data that you need, instead you are literally just receiving the communication from a neighboring compute unit that tells you, instantly, this is the thing that you need for your operation. And this allows for really, really efficient computation and communication.
Wow. So you're building a brain on a chip, right? Because like the neurons and the paths right?
Well, I mean, I did used to work in spiking neural networks.
Oh, wow.
Spiking hardware neural networks. But yeah, so I usually try to avoid the comparison to biological circuits because at the end of the day, we're designing something that's very different. But it is cute and fun to think that we are designing something that is so physical. That is really exciting and very sort of non-abstract. It's very concrete. So that is really awesome.
Wow.
That was great. Thank you, Mark. I'm so excited for this. I can't wait to get my hands on my own little robot brain.
I feel like I definitely need to go back to the drawing board and brush up on my computer hardware after this talk. So if nothing else, you've educated and inspired. So thank you. So Mark, it's really been a pleasure having you on the podcast, and we've definitely learned a lot. So thank you so much for your time.
Thanks, Mark.
Cool. Thanks for having me.
So now it's time for that part of the podcast everybody loves, Banana Data Facts. Today's fact is, did you know, Weyl, that humans share about 50% of our DNA with bananas?
Wow, I had no idea.
Yeah, so next time you're feeling peely, you know why.
Catch you on the flip side, everybody.
Catch you on the peel side. Peel you on the flip side.
That's all we've got for today in the world of banana data. We'll be back with another podcast in 2 weeks, but in the meantime, subscribe to the Banana Data newsletter to read these articles and more like them. We've got links for all the articles we discussed today in the show notes. All right, well, it's been a pleasure, Triveni.
It's been great, Will. See you next time.